Hello, today I'm going to explain you on how to find curve length or arc length by using integral. The topic is from Mathematics 2, Chapter 4. We have used application of integral to find area under the curve before, but now we will talk about length of curve. So what is this length exactly? Okay, if we start from point x1 till x2 here, x2, that length of graph will be our point of interest. And integration calculus teaches us if we have such chains, we can break them into very small, like infinitely small parts. So it will allow us to make approximation. We have used rectangles to find area under the curve, but now we will use tangent line. If the function is differentiable along x1 and x2 arc, we can find the dimension. So let's break our arc into small parts. I will use different color. Let's show these small parts. Here, here, here. All these small parts we can divide our graph into. So I will take any point to draw a tangent line, and I will assume that my tangent line is almost on the graph as it has very, very small change. And I will call this DL. And let's call that at that point, and draw our tangent line. I won't draw full line because we just need very small part of this that we assume it places on our graph. So let's call this small part DL. So this graph is actually comprised of these small parts, and some of them will give us arc length. So it's going to be the arc length, sum of all these small parts, and it's the integral of our small parts. So it's going to be the integral of dl, or we can take any small part here and integrate it, because we need the sum of these parts all on the graph. So delta integral of dl is going to be our arc length. So now we will try to express dl in terms of dx and dy. So to do this, I'll take these 2 points and I'll find this very small part, and I will call this dx. It's very small, like infinitely small, as I mentioned before, and this side is going to be dy. If I draw it in big form like this, if it looks like something like that, dl, dy, and dx. And we all know the Pythagorean theorem, which gives us dl squared is equal to dy squared plus dx squared. Now in integral we have dl alone, so we need to get rid of that square. So we will write whole expression under square root sign, and we will have dl alone. And now we can substitute it in the formula. Now integration sign square root of dy squared plus dx squared, and the borders of our integral is going to be from x1 to x2 as we try to find the length of the curve from x1 till x2. We haven't finished yet. We just need to make some change on formula to integrate. So I will take dx squared out of bracket. So x1 x2 and right orders. So square root dx squared 1 plus dy squared over dx squared. Okay, now I remove this side to another place. Now one last change here. So now we can actually take the x square out of square root as well, and we can write it in such a way. So integral of dl is equal to x1 x2 1 plus dy over dx squared under square root dx. Now the integration of dl will give us L itself. And use another color, maybe green, yellow. Yellow is much better and visible. And L will be equal to integration of x1 from x1 to x2 square root of 1 plus, and what is dy over dx? It is dy over dx going to be f prime x, or derivative of fx. So the final formula is going to be f prime x squared plus 1 under the square root sign. That's our formula for curve length. Thank you for watching.